So I'm going to teach you guys nodal analysis as an algorithm, literally a step-by-step process which you can apply to solve really any circuit. When we learn mesh analysis on Friday, there are a few times that we can't use mesh, but we can use nodal for literally any circuit. So we're going to start off by looking at a circuit that only has current sources in it, because voltage sources make things behave poorly. And then once we figure out how everything works with circuits with only current sources, then we'll add voltage sources in, and then we'll be able to tackle literally any circuit that we could think of. So I'm just going to make up a circuit here. So let's say that I have the following circuit. Like so. Let's say that this is a 10 ohm resistor, this is an 8 ohm resistor, this is a 4 ohm resistor. This current source will be 2 amps, this current source will be 3 Vx, and let's say that Vx will be defined, that's too easy. Vx will be defined as the voltage drop across our 8 ohm resistor. Okay. So this is the circuit that we're going to analyze. Our first step is simply going to be to label our nodes. So I'm going to do that by using different colors like I've done in previous classes. I've got this red node on the top left, this green node on the top middle, this blue node on the top right, and this purple node along the bottom. Our second step is going to be assign a ground node. And so what we are doing here is fundamental to nodal analysis, okay? In order to apply the nodal analysis technique, we have to choose one of our nodes to be the reference for the rest of all of the other nodes. So we are simply saying the voltage at one particular node is equal to 0. That's all that we're doing when we select our ground node. So generally speaking, I choose my ground node to be the node with the most amount of elements connected to it. Okay. I'm going to modify that statement once we include voltage sources in our circuits. So right now, the bottommost node has 3 elements connected to it, and the top middle node also has 3 elements connected to it. So one of those 2 nodes is going to be my choice, or what I would call the better choice, but it does not matter. You cannot choose a wrong node to be your reference node. So it really doesn't matter which one you choose. Typically speaking, the math is a little bit easier if you choose a node where the most things are connected to be referenced. Okay. So you guys tell me which node is our reference node. Somebody said green. Let's do green. All right. A lot of people said, oh, it should be the bottom node. That's perfectly reasonable. Let's do green. Let's see what shakes out. Okay. Our third step is going to be for us to assign our nodal voltages. So what I mean by that is every node that isn't the reference node is going to get assigned a nodal voltage. So I'm just going to put a nodal voltage here, VA, a nodal voltage here, VB, and a nodal voltage here, VC. So each of my nodes has some voltage associated with it. Now I want to explain really quickly what these nodal voltages mean. Okay. So do you guys remember when I talked about the double subscript notation for voltages? So if we had an element and we called this node A and this node B, we could define a voltage as VAB, where the first subscript was for the positive polarity terminal and the second subscript was for the negative polarity terminal, right? Well, nodal voltages are the exact same thing, except that the negative polarity terminal is always ground. So this VA is the exact same thing as if we had written this voltage as VA, with the positive polarity node at node, or excuse me, the positive polarity terminal at node A and the negative polarity terminal at ground. Similarly, this is what the voltage, the nodal voltage VB represents. So the voltage drop across our dependent current source, positive polarity on the right, and our nodal voltage VC is the voltage drop across the 8 ohm resistor, positive polarity on bottom, negative polarity at ground. So, okay, a nodal voltage always has its negative polarity terminal at ground. So we're measuring all of these voltages with respect to that ground. Okay, so my fourth step, and this is only going to be step number 4 if there is a dependent source, is to express my controlling variables in terms of my nodal voltages. So the reason why this is my fourth step, and this is the first step of actually doing any analysis here, or setting up equations and all that kind of stuff, because this is the easiest one to forget. Okay. So what is the controlling variable in this circuit? Vx, okay. I'm calling Vx a controlling variable because Vx controls my dependent current source, okay. So a lot of students say, all right, well, this is where I do it. Absolutely not. You do not define your controlling variables for the source. You define it for what's controlling the source, okay. So the voltage Vx here, in terms of our nodal voltages, is going to be what? Negative VC. Absolutely right. How did you get that, Kieran? Oh, sorry.
Same position as V of X VC is.
Absolutely right. So we could, there's a more formal way that I like to do it here. So I just want to talk about that really quickly. You're 100% correct. Whenever we're expressing literally any voltage in terms of nodal voltages, it's simply the nodal voltage at the positive polarity terminal, which in this case is 0 because the positive polarity terminal is associated with ground, minus the nodal voltage associated at the negative polarity terminal, which in this case is VC. So we could say that Vx is ground minus VC, 0 minus VC, or negative VC, all the exact same thing, okay? So just as a formal description of how to do it, it's always going to work that way. We can express any voltage as the voltage at the positive polarity terminal the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. All right. The next thing that we're going to do, step number 5, is we are going to write a KCL equation at each non-reference node. Okay. So we never write a KCL equation at our ground node, but we will write a KCL equation at every other node. So at node A, what we are going to do is we are going to add these two currents together that are leaving node A and set them equal to 0, because that's exactly what Kirchhoff's current law tells us to do, right? So I'm going to express the current flowing down through the 10 ohm resistor using Ohm's law. So I want the voltage drop over the 10 ohm resistor divided by the resistance of the 10 ohm resistor. Well, the voltage drop across the 10 ohm resistor here with the indicated direction is just going to be VA minus VC. Okay. So I'm going to have VA minus VC divided by 10 ohms. So that voltage drop that I just found is effectively just this drop V10, where the current is going to be flowing into the positive polarity terminal. So I'm writing my equations in this way, and we can think of it as the node that the current starts at minus the node that the current flows to, so that every time I see VA in this expression, it's going to have a positive sign. And every time I see other nodes, they're going to have negative signs. Okay. Now I have to add to this the current flowing to the right through the 2 amp source, which is simply 2 amps. And set this equal to 0. Now we'll perform Kirchhoff's voltage law at node B. So that's going to be these two currents added together. What's the current flowing to the left? Three VX, because the dependent current source tells us it's 3 VX. What's the current flowing down through the 4 ohm resistor? VB minus VC over 4 ohms, absolutely right. Those are the only two currents leaving node B, so I add them together and set it equal to 0. And now I'm going to write my KCL expression at node C. So that's going to be this current up plus this current up plus this current up. So what's the current flowing up through the 10 ohm resistor going to be? VC minus VA over 10 ohms. Thank you, Emily. The current flowing up through the 8 ohm resistor, VC over 8 ohms. And finally, the current flowing up through the 4 ohm resistor. Absolutely right. VC minus VB over 4 ohms. And so now we have written 4 equations and we have exactly 4 unknowns, our 3 nodal voltages as well as the voltage Vx. So because the calculator that Nicholas Stevens was so kind enough to let me borrow today can only solve 3 equation, 3 unknown systems, that means we're going to have to substitute in, or at least I'm going to have to substitute in, this relationship of Vx is equal to negative Vc into here, right? So for all of us that have 3 equation, 3 unknown calculators, we're going to have negative 3 Vc plus Vb minus Vc over 4 ohms is equal to 0 as our second equation. And now we're at our last step, which is simply to solve our system of equations. Let's see, this is step number 6. So let's see, I'm gonna remember where the equation solver is here. 5. This is a 3 equation, 3 unknown system. So I'm gonna consider this guy right here to be equation 1, this guy right here to be equation 2, and this guy right here to be equation 3. So my coefficient for VA in my first equation is just 1 over 10. My coefficient for VB in my first equation is 0. My coefficient for VC in my first equation is negative 1 over 10. And my constant term is going to be negative 2 because I need to move it to the opposite side of the equal sign as my variables. Okay. In my second equation, my coefficient for VA is 0. My coefficient for VB is positive 1/4. And my coefficient for VC is negative 3 minus 1/4. And I'm literally just typing that coefficient into my calculator in that form and letting it do all of the simplification for me. My constant term is equal to 0. Now I'm on to my third equation. My coefficient for VA is negative 1/10. My coefficient for VB is negative 1/4. My coefficient for VC is 1/10 plus 1/8 plus 1/4. And it looks like my constant term is 0. Solving this system, assuming I put everything into my calculator correctly, I got VA to be negative 444 over 23 volts. VB to be 208 over 23 volts. And VC to be 16 over 23 volts. Did anyone else get similar numbers when they solved the system? Good deal. All right, so we've solved for all of our nodal quantities. Now we can solve for literally anything else in the circuit, right? So we already have an equation saying that Vx is equal to negative Vc. So from the jump here, we could see that Vx is simply negative 16/23 of a volt. But what if I wanted to determine the power supplied by my 2 amp current source? How would I figure that out? So let me erase all these little arrows here because they're just going to get in the way, right? So if I want the power supplied by my 2 amp source, it's going to be the current flowing through my 2 amp source multiplied by the voltage drop across my 2 amp source, where let's call this V2A. Let's do it in green. I want the current to flow into my negative polarity terminal and out my positive polarity terminal, right? So in this case, that power is going to be 2 amps times V2A, where V2A is simply 0 minus VA. .444 over 23. .888 over 23 watts. Okay. What if I wanted to know the current through the 10 ohm resistor? Exactly right. VA minus VC over 10 ohms, which would come out to be whatever the heck it comes out to be, all that kind of stuff. Once we know the nodal voltages, we are one step away from figuring out literally any other quantity that we could be interested in. We're one step away from figuring out any power, one step away from figuring out any voltage that we don't already know. So I could figure out what the voltage drop is between this node and this node if I wanted to, for whatever reason. That could be a thing. One step away using Ohm's law from figuring out any current, right? So once I've got all of my nodal analysis done, then I can figure out literally any other possible quantity that I could be interested in just using those nodal voltages and Ohm's law and the power relationship. All right. So let's mess with things now and include voltage sources. Yes. Right, so I said 0 minus VA because the positive polarity terminal was associated with ground or 0. If this instead were, let's say VD, it would be VD minus VA is that voltage. Mhm. All right, so let's say that we have a 9-volt source here. A 10 ohm resistor here. Two amp source here. A 5 IX voltage source here. Let's make this a 6 ohm resistor. No. I'm gonna wind up with too many unknowns if I do it that way for this particular calculator. 2 ohm resistor here. All right. So we have voltage sources in the mix now. So our first step is going to be exactly the same. we are going to identify and label our nodes. So I've got this red node on the top left, green node here, blue node here, pink node on bottom. Step number 2, exactly the same. Select our reference node. Fantastic. Yep, I need to figure out what IX is going to be. So let's make IX that current. So whenever I have voltage sources in my circuit, I typically try to choose my reference node to be the node at which the most voltage sources are connected to. Well, in this case, since my voltage sources are at different parts of the circuit, there isn't, at most I'm going to be able to touch one voltage source with my ground node. So here, then I would go back to my default of the node that the most elements are connected to. And it looks to me like the pink node is connected to 4 things. The green node is connected to 3, the blue node is connected to 3, and the red node is connected to 2. So pink is, to me, the most logical choice. Don't have to choose that, but it's the one that I'm going to choose here. Step 3, we will assign our nodal voltages. So let's call this VA, VB, and VC. Excuse me, like so. Step number 4. Is to express our controlling variables in terms of our nodal voltages. You got ahead of me, Emmeline, so I'm not sure. Nodal voltages. So, ooh, what the heck happened there? VA minus VB over 10, is that what you said? Yes, then that is absolutely correct. VA minus VB over 10 ohms. That's our only controlling variable. All right. So we're going to skip what I want step 5 to be for right now, because I'm intentionally going to show you why voltage sources mess things up here. So we're going to backtrack here in a moment. So we're going to move along to step number 6. And again, I'm not going to give it a name just yet. We're going to do it, and then we'll talk about that here. Okay. So if we tried to write a KCL equation at node A, we would run into a little bit of a problem. We would have this current down and this current to the right. The current to the right is the exact same thing as IX, so we know that that's going to be VA minus VB over 10 ohms. No problem there. The current flowing down, however, is just the current flowing through a voltage source. And unfortunately for us, there is literally no way for us to describe the current flowing through a voltage source in terms of our nodal voltages, okay? So instead, what we are going to have for this particular case is simply a voltage relationship equation, okay? So to explain things a little bit better here, we're going to jump ahead and we're going to write our KCL equation at node B, okay? So at node B, we're going to have this current, and this current added together. And we're going to wind up having a similar problem, but there is a way to fix things, okay? So at node B, we're going to have VB minus VA over 10. Plus, or actually minus 2 amps. And then plus what I'm going to call I dependent from left to right. So that just represents the current flowing through my dependent source from left to right. Okay. There's no, because I have a voltage source here, there's literally no way that I can express it in terms of my nodal voltages. So I've introduced another variable, which might be problematic. Now I'm going to write my KCL expression at node C. That's going to be this guy, and this guy added together. And so my current to the left is going to be I dependent from right to left. My current flowing down is going to be VC over 6. And my current flowing down and to the right is going to be VC over 2 ohms. So these two individual KCL equations have that I dependent current in them, but they're flowing in opposite directions, right? So what I'm going to do is I'm going to add these KCL equations together. So let me explain why I can do that, okay? So you might be looking at me incredulously, some of you are. My KCL equation at node B is equal to 0. My KCL equation at node C is equal to 0. So I would argue, and I'm pretty sure I'm right here, that 0 plus 0 is equal to 0. So I can add these two equations together with absolute impunity and nothing bad will happen. So if I add these two equations together, what I'm going to wind up having is VB minus VA over 10 ohms minus 2 amps. My I dependents are going to cancel each other out because they're flowing in opposite directions. Plus VC over 6 ohms plus VC over 2 ohms will be equal to 0. Okay. So that's the result of me adding those two equations together. Now I'm going to go back to my diagram and I'm going to identify something. Okay. So I'm going to draw a circle, loop, a blob, or whatever around my voltage source here. That KCL equation that I just wrote, this guy right here, represents the currents that are leaving this voltage source. So I'm going to call this quantity a supernode. All right. While I'm at it, I'm going to erase this current. I'm going to erase this current. The current's flowing through the voltage source because internal to that supernode, they're going to be flowing in opposite directions and cancel each other out. So I have this combination of nodes, right? So my supernode contains node B and node C. And I can write a single equation that gives me all of the currents that are leaving that supernode. And it allows me to avoid writing expressions for the currents that are flowing through the voltage source, right? So I have two nodes here. I have a KCL equation. Now I need another equation, right? So let me tell you what step 6 is now. So write KCL equation for each supernode that does not contain the reference or the ground node. I'm going to move this stuff down to give me a little separation here. So I'm going to call this equation right here KCL at supernode BC, because that's what it represents. How am I going to get another equation for nodes B and C? If there are two nodes in that supernode, I should be able to get two equations out of it. Anybody have any thoughts whatsoever? Spitball stuff. Ohm's law. Ohm's law works for resistors. Is the voltage source a resistor? Nope. So definitely spitballed something, but not correct. So it works sometimes. All right. So I need to give myself even more room so we can actually write things here. That's not what I wanted to have happen. So we have that voltage source, right? 5ix. What's the nodal voltage at the positive polarity terminal? VB. What's the nodal voltage at the negative polarity terminal? There's our other relationship. For every voltage source in our circuit, we are going to have a voltage relationship equation. All right. So we're going to write a voltage relationship equation for every supernode, and literally every voltage source forms a supernode. Okay. So we have another supernode over here around our 9-volt source. So we need a voltage relationship equation for that. So what's that voltage relationship going to be? Yep, so 9 volts is equal to VA. All right. Now let's look back at the wording for step number 6 again, right? Write a KCL equation for each supernode that does not, and I put emphasis on the does not, contain the reference node, right? So our supernode for our 9-volt source is between node A and ground. So we're not going to write a KCL equation there because it's pointless. We have one node and ground. We have one equation, our voltage relationship equation. We don't need anything else. Okay. All we need is that voltage relationship equation. So as it turns out, we're done. We have exactly 3 equations for exactly 3 unknowns. And well, actually we have 4 equations for 4 unknowns because Ix is also an unknown here. If this particular circuit had more nodes, we would include a step number 7. Write KCL equations for all remaining non-reference nodes. There aren't any. And step number 8 is simply to solve our system. So I'm going to have to do a substitution here. So let's see, 5Ix is let's see, 5/10 is 1/2. So that's going to look like VA minus VB over 2 minus VB plus VC is equal to 0. When I substitute in 5Ix, you guys follow the algebra? Did I screw something up there? So 5/10 is 1/2. 1/2 times VA minus VB gives me this thing. I move VB to the left-hand side of the equal sign. I move VC to the left-hand side of the equal sign and set everything equal to 0. So that's one equation. My second equation is literally just going to be VA is equal to 9. My third equation is here. Now I can solve for these 3 nodal voltages. So my coefficient for VA in my first equation is 1/2. My coefficient for VB is -1/2 minus 1. My coefficient for VC is +1. My constant term is 0. In my second equation, my coefficient for VA is 1. My coefficient for VB is 0. My coefficient for VC is 0. My constant term is 9. In my third equation, my coefficient for VA is -1/10. My coefficient for VB is +1/10. My coefficient for VC is 1/6 plus 1/2. My constant term is 2. And solving, I get VA is equal to 9 volts, big surprise there. VB is equal to 59/11. And VC is equal to 39/11. And from here, I know everything that I could possibly know about my circuit within 1 or 2 steps. Okay. So, would you guys like me to make up another example problem, or do you want to work on the in-class assignment? Kieran? Yes, sir.
Talk about the I dependent, why we had the equation not do I dependent. Or like do go to the right I dependent.
For the previous problem?
No, for this problem.
What is I dependent?
It's a variable.
Oh, yeah, sorry. So the first one was this guy right here, flowing through the dependent current source from left to right. The second one is here, flowing through the current source from right to left. When I add these two equations together, I have equal currents flowing in opposite directions, adding to each other, which means they just cancel out. So if I have 5 amps to the left plus 5 amps to the right, it's 0.
I guess my question would be why are they both like hanging on to these one I dependent in one direction? And if I'm a negative, I'll do that concern.
But how can I express it in terms of nodal voltages at all? That's the problem. The-
My main question is when you add the equation,
Mhm.
like mathematically, it doesn't work out, I guess. Like if you add-
So, okay, so you're saying I dependent, so I'm gonna have I dependent left to right plus I dependent right to left. I have to understand it because they're in opposite directions, yeah. So I dependent right to left is negative I dependent left to right. Yes, we're adding them because we want the currents leaving that supernode. So instead of saying, like when we're writing our KCL equations, in every other case where we don't have a voltage source, we're saying the current leaving this one node is equal to 0. Now we're saying the current leaving this combination of nodes is equal to 0. So it's just following suit with writing KCL leaving a node. So that's why we're adding them together. You absolutely could set them equal to each other because 0 is equal to 0 as well. And that's just going to make signs wonky and all of that kind of stuff because you're going to have things that you would associate with having a positive sign because it's leaving that node now have negative signs. So the short answer, and you may not like this, is because it's going to make the math nicer because there's going to be less spurious negative signs all over the damn place. Yep. Any other questions? So I will ask my question that I asked a moment ago. Do you guys want me to make up another example problem or do you guys want to start working on it? Another example problem. All right. With or without voltage sources? Let's do with voltage sources. Okay. You know what? Somebody come up here and draw a circle. Sure, that's fair. Okay, we'll do one of the Wehrbork problems. All right. You guys are talking a lot and it's giving me a worse headache, so please dial it down a smidge. What homework set were you guys? All right, so let's take a crack at homework 5, problem 3. Do you have a preference for A or B, or excuse me, B or C? C, all right. So we're going to take a crack at C here. That wasn't paying enough attention. So I have some resistance. R2. And for me, R2 is 29 ohms. Then I have a voltage V2, which is 43 volts, positive polarity on the left. Then I have a 2Vx source direction up. Vx Positive polarity on the left, R1 is 10 ohms. Then I have another voltage source here, positive polarity on top, B1 is 26 volts. All right, and we're just solving for Vx, is that correct? All righty, so first thing I'm going to do is identify my nodes. So there's 1, there's 2, there's 3, there's 4. Step 2, assign my ground node. I have 2 voltage sources, they're not connected to each other. Green node is connected to 3 elements, purple node is connected to 3 elements, red is connected to 2, blue is connected to 2. You guys tell me where to put ground. Purple. All right. So let's call this VA, VB, and VC. What's my controlling variable relationship going to be? Vx is equal to VB minus VC. I agree. That's the only controlling variable we have, so we're done. I have 2 voltage sources, so I'm going to have 2 voltage relationship equations. What are they going to be? So 26 volts is equal to VC. 43 volts is equal to VA minus VB. Okay. This is a supernode. This is a supernode. The supernode for VC obviously contains ground, so I don't write a KCL equation for that. The supernode for the 43 volt source doesn't contain ground, so I'm going to have, bless you, this current plus this current plus this current, set it equal to 0. So what's the current flowing down through my 29 ohm resistor? What's the current flowing down through my dependent source? Minus 2 Vx. What's the current flowing to the right through my 10 ohm resistor? Solve it. You're done. If you have a Casio 991, your variables will be VAB, VB, VC, and VX. If you have a Casio 115 or a TI 36X, simply substitute in the relationship for VX into this thing right here, and then solve. Want to take a crack at another thing? Part B on the same question, sure, why the hell not? Yeah, let's see. So I1 is negative 3.2 amps up, so I'm going to draw it as 3.2 amps down because I don't like negative signs. Then we have R1, which was 10 ohms in parallel. Then we have our voltage source, 5IY, positive polarity on the right. Here's R2, which for me has a value of 29 ohms. This is my current IY. I2 is negative 6.2 amps up, so it's going to be positive 6.2 amps down. identify my nodes. Which one do you want to be ground? The blue, the one at the bottom, okay. So let's call this VA. Let's call this VB. Just for the sake of argument, we're gonna go ahead and identify that supernode. My controlling variable equation is going to be what? IY is equal to VB over 29, absolutely right. I have a voltage source, so what's my voltage relationship equation? All right. Now I'm going to write my KCL equation for my supernode. So that's going to be this current plus this current plus this current plus this current. So that's going to look like 3.2 plus VA over 10 plus VB over 29 plus 6.2 is equal to 0. Solve it. And I won. So that's why I drew my arrows in the opposite direction. I don't like negative numbers. I screw up when I have negative numbers.
Just come up with one that is just. About this triple up.
Yeah.
That's the question that's gonna be on.
I mean. Speaking of what's going to be on the test. Today. 221. Exam 1 review material, old exams. Let's see. Something like this, you could do nodal analysis on. I see 1, 2, 3 nodes. Nothing wild or crazy there. 1, 2, 3. Yep, you could do nodal analysis for that one if you were so inclined. You do nodal analysis for this one. Technically could do it for this one, but it wasn't my intention. I mean, you can throw nodal analysis at pretty much anything if you want to. Whether or not it's a smart move is an entirely different discussion, but yeah. So anyway, all right. Any other questions for me, or do you guys ready to, or excuse me, or are you guys ready to work on your in-class assignments?